Alright, welcome to Physics 150, Chapter 11, Sections 7 to 10. By the end of this podcast, you should have a better understanding of the principle of superposition, reflection and refraction, interference and diffraction, and standing waves. Alright, so let's get. Alright, this is what's called a traveling wave. And it's a traveling wave because it moves in time. So this is what a traveling wave looks like. So what we're going to do is put more than one of those in our medium at a time and see what happens. Alright, this is the superposition principle. When you have two or more waves overlapping, the net disturbance at any point is the sum of the individual disturbances due to each wave. So this equation down here, Y nu, is the mathematical description of superposition for three waves in the same medium at the same time. So you add them all up, and that equals the new wave. Now, what I want to show you is what this looks like. So I have traveling pulses here, and as they move, you can see that they're interfering right there, and that by the principle of superposition, I can change how they're doing. So if I move this forward, you see when they're over top of each other, they have a big displacement. So they're interfering what we call constructively. And if I let time goes on, they decrease because they get farther apart and they're not interfering anymore. And if I bring them back, you can see that they have some sort of type of superposition there for all these waves. And that is an example of superposition. Alright, so let's try a problem. Here you got two pulses traveling on a chord at time t equals 0, moving towards each other. The speed of each pulse is 40 centimeters per second. Sketch the shape of the chord at these three times. So what we're going to do is okay, so what we're going to do is we know at t equals 0.54 seconds, I want to find its change in position from its original position. To do that, I have to take its velocity times the time. So 40 seconds, 40 centimeters a second times 0.15 seconds equals 6 centimeters. I do it for the other time, I get 10 centimeters. I do it for the last time, I get 12 centimeters displacement in the direction of those velocities. So what would the wave look like? What I have to do to show you the wave is look at this. So we found out it should be displaced 6 centimeters. So what I'm going to do is use the smaller wave first. It should be displaced 6 centimeters to the right. So the green arrow shows the displacement. And then I redraw the wave. And I'm measuring from the peak here. And then the same thing for the bigger pulse over here that's moving to the left. It's supposed to be displaced 6 centimeters. And then I redraw the wave. You'll see down here that the pulses are just starting to interact by my drawing. And yes, my drawings aren't exact, but it's the best I could do. So these waves should overlap and grow a little bit higher, but it's so small I didn't draw it in there at this time. So let's look at a different time. So here, what we want is the wave has been displaced 10 centimeters from its original position. So that puts the smaller wave at 20 centimeters. It puts the bigger wave at, and so it would have look like it's traveled here. The bigger wave is going to be displaced 10 centimeters, and that's also going to put it at 20 centimeters. So these things are going to add up, and if we add them up, it looks something like this. And so this would be the superposition of these two pulses at t equals 0.25 seconds. And then as we move farther in, again, now the little wave is displaced to 12 centimeters, so it's going to be here. The bigger wave is displaced 12 centimeters. You see, we still have some overlapping. So what we have to do is add up all the amplitudes. So I take this point for the bigger pulse there. I add it to this point for the smaller pulse, and they will add up to look like this. And the pulse will look something like that at t equals 0.3 seconds. All right, when we're dealing with waves, we have interactions called reflections or refractions. We're going to start with reflections first. What is a reflection? If the wave hits a boundary between two mediums, then a reflection occurs unless the mediums are exactly the same thing. They have to be two different mediums. So water and air, ropes with two different mass per unit lengths, something like that. Glass and air. The reflected wave carries some of the energy of the incident wave, travels backwards from the boundary. A reflected wave will be inverted or have a phase shift of pi or 180 degrees if the boundary is fixed. Well, when a wave reflects off a medium, the wave can reflect back opposite its initial velocity, or I should say backward into its original medium, or it can transmit into the new medium. So when it transmits into the new medium, some of the energy is transmitted in this new medium. When that transmission occurs, you have a change in the wavelength at the boundary of these two mediums. And what doesn't change is the frequency has to be the same for both the incident wave and the transmitted wave. And so we get this relationship that the frequencies of these two waves have to be equal, and by definition, you have the velocity of the incident wave and the wavelength of the incident wave is the velocity of the transmitted wave and the wavelength of the transmitted wave. And they have to be equal in this ratio. We're using the idea that the velocity of any wave is equal to its frequency times its wavelength. Well, what is refraction? Well, refraction is when you have a transmitted wave. It just doesn't have a different wavelength. As you can see here, these are the crest of the waves. The blue lines are the crest. And you see as it enters water, they're closer together, so the wavelengths are changing. Now, it just doesn't change its wavelength. It'll also change the direction the wave is traveling. And this change in direction is what we call refraction. And you can get an angle of refraction and an angle of incidence, where the normal is a line perpendicular to the boundary of the two mediums. So when you have multiple waves traveling in the same medium, you get what we refer to as interference. And to figure out the interference, we have to use the principle of superposition. And you get the most dramatic interference if the waves are considered to be coherent waves. Coherent waves have the same frequency and maintain a fixed phase relationship between the different waves. And incoherent waves have random phase relationships. So if you have the interference of coherent waves, you get constructive interference if the amplitudes of the waves add together, so you get a maximum displacement. And we call it destructive interference when the amplitudes of the waves are subtracted. in this manner. And these interference patterns, you can get these interesting interference. All right, a type of interference is called diffraction. And what is diffraction? Well, by definition, diffraction is the spreading of a wave around an obstacle. If you look at this boat here, it has oncoming waves hitting it, and you can see the boat blocks some of the waves, but the waves tend to also end up behind the boat, right? There is a void, but some get bent around the boat, this obstacle, and are end up behind it. You can see this other picture here. The difference is the wavelength over here is much larger, and you can see the diffraction is much larger. It bends much more when the wavelengths are larger than they are if they're smaller. This is the reason you can actually hear sound around corners. It's because the sound wave gets bent around the obstacle. All right, one of the most interesting effects of interference is what's called a standing wave. Standing wave has nodes and antinodes. A node is basically defined as zero displacement. When you look at this animation, if you point to the waves that are not moving at all, and an antinode is where you get maximum displacement or a lot of displacement from equilibrium, or basically more than zero. So I'll show you this animation of standing wave. Here goes. And so you can definitely see points in this wave that are that are not moving, okay, and then points that get very large. So this is a point of a node. This is another node. This is a third node. This would be considered an antinode. This is an antinode. This is an antinode, and this is an antinode. So and standing wave will oscillate back and forth like this. And this wave does not look like it's moving left or right, but it looks like it's moving up or down. And this is why we call it a standing wave, because it doesn't look like it's moving, it's standing. All right, how do we calculate the properties of the standing wave? Well, the first frequency that produces a standing wave is called the fundamental frequency, and it produces a wave pattern that looks like this. And let's call the distance between these two nodes length L, and they have one antinode and two nodes in the first fundamental frequency. So this is the maximum amplitude as it's above equilibrium, and this is the maximum amplitude below equilibrium. Like these are stationary or frozen in time, like I took the picture and frozen in time. Well, what we can do is we know the frequency of a wave is equal to its velocity divided by its wavelength. Well, what is its wavelength? Well, if we look at this, this looks like half a wave there. You can imagine it coming out here. So it's about half a wave showing up there. So what I say is that L, this distance L is equivalent to half a wavelength. So if I solve for the wavelength, it is 2L. And so the frequency of the fundamental is the velocity of the wave divided by 2L. Well, we have harmonic. The first harmonic has two antinodes and three nodes. Well, what is L? L is still this distance. How many half a wavelengths do you see? I see 2. So now L is equal to 2 half a wavelengths, or a wavelength is just equal to L. And so the frequency is V divided by L. And then we have the second harmonic, and in the second harmonic, how many half a wavelengths do you see? I see 3 half a wavelengths. In this case, lambda would be equal to 2L divided by 3. And then even if you go to the third harmonic, you see how many half a wavelengths here? I see 4. That means lambda L is equal to 4 half a wavelengths, or lambda is equal to uh, L divided by 2 in this case. So do we see a pattern here? I have V divided by 2L. Here I have 2 half a wavelengths. So that would be like 2V divided by 2L, which comes out to be V divided by L. Here I have 3 half a wavelengths. So if you solve this, you would get 3V divided by 2L. And then here I have 4 half a wavelengths. So you solve this, and I would get 4V divided by 2L, and that would come out to be 2V divided by L. So you get, if you want to find a frequency for different harmonics, you get this formula that N is the number of half a wavelengths that show up, or the number of antinodes that show up in the standing wave, and you multiply that times V and divide by 2L, or twice the length of the wave on a string. And that is standing. All right, let's try to use some of these ideas to solve a problem. I have, the problem is, in order to decrease the fundamental frequency of a guitar string by 4%, by what percentage should you reduce the tension? In order to do this, I know the velocity of a wave on a string is equal to the square root of the tension divided by its mass per unit length. What other information I know? Well, it's the fundamental frequency, so I need to know the length of the string. I also know that the wavelength is equal, or the velocity is equal to its wavelength times the frequency. I also know that the length of the string will not change with the guitar, so lambda is unchanged. Since the string of the guitar won't change, mu is also unchanged. So if I do a new calculation and to find my new velocity, I would have to know my new tension, and I have my old mass per unit length. That should be equal to my original wavelength. The length is not changing, it's the fundamental, times my new frequency. So what can I do there? Well, if I divide both equations, several unknowns disappear. The lambdas will cancel, and the mass per unit lengths will cancel. And what my equation turns into looking like this. Now I have the frequency depending on the square roots of the tensions in the string. So I still have that expression. So I'm going to put in my new frequency has to be 4% lower than my old frequency, so it's going to be 96% of my original frequency. If I plug that in there, you'll find out that the original frequencies will cancel, and I get the number 1 over 0.96. So now, just take that and solve it. I want to get rid of the square root, so I'm going to square everything on both sides, and that gives me this equation. Now I can solve for the tensions. So I'm going to cross multiply. I'm going to take the 0.96 squared and multiply it times my t. I'm going to take my tn and multiply it times my 1. If I do that, I get this expression. So if I find the square root of this number, it comes out to be 0.92, or 92% of the original tension. So I need to reduce my tension by 8% in order to be able to get a new, decrease my fundamental frequency by 4%. Okay, that's the end of the podcast. See you next time.